Density and pressure. First of all, the definition of density. Density of any substance is measured by using the following formula. Density equals to mass divided by volume. Density is expressed by the letter rho. Mass is expressed by the letter m. Volume expressed by v. The unit of density is kg per meter cube or gram per centimeter cube. Mass is measured in gram or kg, kilogram. Volume measured in centimeter cube or meter cube. The most common unit of density is kg per meter cube, kilogram per meter cube. So we can block it in a box with the formula of density and using the symbols. Find out density. Rho equals to m by v and density equals to mass by volume. To measure density of any substance, we can use this formula. Look at this. There is here the units are given, kilogram per meter cube, and it's also measured in gram per centimeter cube. Now there is an example here. A piece of iron has a mass of 390 kg and a volume of 0.05 meter cube. What is its density? So this is what? This is mass. I can say this is m and this is volume v. We have to find out density. So if we put mass by volume, then we get density 7,800 kg per meter cube. This pyramid structure also is very useful to remember the formula. The density equals to mass by volume. The density equals to mass divided by volume. Volume equals to mass divided by density. And mass equals to density multiply volume. So you can remember any one of them if you can remember this pyramid diagram or triangle diagram. This is also called triangle diagram or pyramid diagram. Now we are here to find out the practical experiments, how to find out density of different substances, especially for regular shaped object, this one A, and for irregular shaped object, this one B. Look at this. Mass, we need to find out mass, we need to find out volume. Mass can be found by using electronic balance. You can find out mass of any object. The problem is volume, right? This kind of cubic object, we can find out volume by using the formula length multiply width multiply height. This kind of regularly shaped object, we can find out volume using the formula length multiply width multiply height. And we can find out mass by electronic balance. And we can use density, mass by volume formula. But what would happen if the object is irregularly shaped? Look at this diagram. What would happen if the object is not regularly shaped object? For example, a rock. It can have different shapes. So what would we do? We get water. We use displacement can. This is displacement can. I can level it for you. This is displacement can. This is a very thin thread. This is measuring cylinder. This is water. This is water. And when you submerge the rock into this water. This water was just this much big, this much level it has. So putting the irregular shaped object, the water would overflow through this way, through this channel, and the overflowed water would be collected in this measuring cylinder. The volume of water overflowed equals to the volume of the irregular shaped object invented by the scientists. I repeat again, the volume of the water overflowed when you submerge this irregularly shaped object into the displacement can filled water. The volume of the water overflowed measured by the measuring cylinder is the volume of the irregularly shaped object. So this is thread. This is displacement can, water, measuring cylinder, and this one is displaced water. The thing is that to measure the volume of displacement can, and which is submerged into water, thread, connected of volume of the so we can measure the volume of any irregular shaped object this way. Then we measure the mass like using electronic balance, and we use the equation density equals to mass by volume, so we can find out the density of any object. And while measuring uh, volume from cylinder, we must get the reading from the meniscus of the water level to avoid parallax error. You see here parallax error. Any kind of distance measurement error is called parallax error. Here there is another math given. Look at this. Example 2. The mass of 50 cm cube of a liquid and the measuring cylinder is 146 gram. So the volume of liquid is 50 cm cube. Now we need to convert it into meter cube. Is the volume V. We must convert it into meter cube. How? This way. That 100 centimeter equals to 1 meter. So if you cube in both sides, 100 cm equals to 1 meter cube. What would happen? 100 cube equals to 1 meter cube. Right? So 50 cm cube means 50 divided by becomes 0.5 meter cube. So this is the volume V. So measuring cylinder has a mass of 146 gram. The mass of empty measuring cylinder is 100 gram, including the liquid is 146 gram. Subtracting would give the mass of the liquid. So if we subtract, we get 146 minus 146 gram and divided by 1000, it would give kg. So divided by 1046 divided by 1000, we can convert it into kg. 0.046 kg. So this is mass M. We know M, we know V, we can find out rho. The question is to find out the density. So this is the density, 920 kg per meter cube. Very simple math. Then we will read pressure under a solid. If we put an object anything under an object, the object would feel pressure. And the unit and the equation of pressure is pressure equals to force divided by area. To find the pressure, we can use the equation pressure equals to force divided by area. Force is expressed in newtons, area is expressed in square meters, and pressure is expressed in pascals. If force is 1 Newton and the area of the object is 1 square meter, then pressure would be 1 Pascal. And it is also called 1 Newton per square meter. 1 Pascal is equivalent to 1 Newton per square meter. So we can underline pressure is defined as force per unit area. Force is measured in newtons and area in square meter. So 1 Pascal is equivalent to 1 Newton per meter square. Pressure is expressed in small lowercase letter p, force in capital F or uppercase letter F, area in uppercase letter A. So this is the formula of pressure. So what does it mean by 10 pascals of pressure? Pressure means 10 newtons of force is applied on 1 meter square of area. What would mean by 110 kilopascal of pressure? 10 multiply 1000 Newton of force is applied on 1 meter square of area. All right. So there is another math here. An elephant has a weight of 40,000 Newton. Look at this. Elephant, it has weight of 40,000 Newton and her feet cover a total area of 0.1 meters square. Her feet cover how many foot? An elephant has 4. So the total area covered by her feet, it is 0.1 meters square. What would be then the pressure by the elephant? Pressure by the elephant would be pressure equals to force by area. This is force, 40,000 Newton here. Then you can see force 40,000 Newton, area is 0.1 meters square, and putting the values 400,000 Pascal or 400 kilopascal it comes. Then the pressure by the elephant. A woman weighs 600 Newton and the total area of her shoes in contact with the ground is 0.0015 meters square. Very small. Who exerts greatest pressure on the ground? Who means the elephant or the women? We have to compare. So first of all, we found the pressure of the elephant. Now we need to find the pressure of the women. Same equation, pressure equals to force by area, force equals to 600 Newton, weight of the women. Here, weight of the women is the force. Remember. And weight of the elephant is the force. 600 divided by 0.0015 meters square. Similar results. Look at this and look at this. So they would exert similar pressure, equal pressure. Equal pressure they exert because calculation shows both give similar pressure, that is 400,000 Pascal. All right. So it doesn't matter that an elephant, a big body animal, would give greater pressure than an women like this, because the women weights is all 600 Newton. You know that women weights is 600 Newton. So what is the mass of the women? Any idea you have? What we know, weight equals to mg. Weight is 600 Newton equals to m multiply g. The value of g is 10. In our world Earth, it is fixed. So 600 divided by 10 equals to 60 kg. The women weights the women mass of the women is 60 kg. What? Very high value. So what is the mass of this elephant? 40,000 divided by 10. 4,000 kg. So look at the mass of the elephant. It's 4,000 kg, and look at the mass of the woman. She is only 60 kg. But area is bigger under the feet of the element. I repeat, area is bigger under the feet of the element, and that's why pressure decreased. Greater area elephant, and so pressure decreased, we can say. When area increased, force remains constant, pressure decreased. All right, look at this. This is a caterpillar truck, and this is the feet, large feet of a camel. They do not sink. The caterpillar track, it does not sink into muddy ground or soft ground, and the camel, it does not sink on desert because they have greater area under the caterpillar track and under the camel's feet. As the area is greater, so weight spread it over a large area and pressure decreases. Pressure decreases. That's why they do not sink. Pressure under the caterpillar track or pressure under the camel's feet is relatively low, and they do not sink into muddy ground or soft ground or in desert. Then when we cut something by using cutting tools like scissors, bolt cutters, knives, we need to put high pressure. And we put high pressure using very sharp knives because it has very small area. The force we put and the pressure becomes high because of very small area. High pressure works, and scissors or bolt cutters, knives work easily to cut anything. So you must read this paragraph too properly. Now we'll read pressure in liquids and gases. When liquid is not, for example, when liquid is stationary or it is not moving or flowing, then pressure inside liquid, it acts equally in all directions. Pressure inside liquid, it acts equally in all directions. For example, like this, look at this. This is a submarine. Liquid gives pressure from all directions to this submarine. And similar rule applies for gas. Gas also gives pressure from all directions. Gas also gives pressure from all directions. Look at this. This is a cylinder, and it has like many holes at the bottom. It is filled with liquid. When these holes are opened, liquid is coming out from each and every hole similarly. It means that they are getting similar pressure inside the cylinder. That's why they are coming out similarly, falling out at similar distance. So very important line that gas also exert pressure on things around them. The pressure exerted by the atmosphere on your body is about 100,000 Pascal. So remember this pressure. The pressure exerted by the atmosphere on our body is about 100,000 Pascal or 100 kilopascal. And the pressure inside our body is also same. Inside and outside, similar pressure. That's why we do not notice it. We do not notice this high pressure. Otherwise, 100 kilopascal is a very high pressure, but we do not notice because inside and outside the pressure is equal because we live in atmosphere, and atmosphere means we are always inside gas. Gases are everywhere, inside our body and outside our body. And the gas gives equal pressure inside and outside. Then there is a demonstration. The demonstration has been, it had been done by greater scientist Van Guericke in Germany in 1654. The experiment was actually done by large balls, metal balls. What he did, he pumped out all the gases from inside the ball, and then he cut the ball, pumping out all the gases, and he joined the ball. Look at this ball. Then he used two teams of horses. Look at this horse cart. They tried to pull the ball by uh, tying ropes through these handles to separate them, and they could not. They failed because when there was gas inside the bowl, there was inside and outside pressure that was equal, so we can easily separate them. When you and me, we can separate it. But when all the gases are actually thrown out or brought out, then the gaseous pressure remains only outside. And due to this outside gaseous pressure, now it is not possible to separate these two halves of the bowl. Though if it is even used like horse or horse carts, it doesn't matter. So it is so strong. So just think about that the gaseous pressure from outside, how strong it is, that it cannot be separated by horse. Now, this is a simple math here. A laboratory set of Magdeburg hemispheres and a surface area of 0.045 meters square, or the total force on the outside of the hemisphere. So force equals to pressure multiply area, and atmospheric pressure is 100,000 Pascal that I said. 0.05 meters square area is given here. So force is 4,500 Newton. Now pressure inside this cylinder, now there are different holes and different heights. Pressure relates with heights. The greater, if you measure height from this place, if you go down and if you measure the height, like this is hole number 1, this is hole number 2, and this is hole number 3. So number 3 has the greatest height among them. Then number 2, then number 1, height of the liquid. As number 3 has the greatest height, liquid comes out with greater pressure and it falls further. Liquid comes out with greater pressure and it falls further because hole number 3, it has greater height from the water level of the top. Okay. So we got equation, important equation here. The pressure difference is actually depends on height, density, and gravitational field distance. So mark it. Pressure difference equals to height multiply density multiply gravitational field strength. Greater the height, greater would be pressure. There is another simple math. It is solved here in example 5. Then you can do easily finding out the pressure, H rho G formula to use. Here H is given 0.74 meter. Density of mercury is given 13,600 kg per meter cube, and gravitational field distance G is 10 always. So it is 100,640 Pascal. So this is almost all about this chapter. So I request all the students to read properly all these documents and things so that you can understand.